On my last video, I received a question about averaging on the traces, which I think is important enough to try to answer and respond to in the video. So I try to articulate a response to that. I also have a program that I've put together for programming the EEPROM I'm using on the breadboards for the control logic. I'll give a walkthrough of that. I'm going to test the TommyPROM finally, and we're going to get to a point where this CPU is free running, and it's going to include some debugging to get there. Let's get right into it.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
I need some way to maintain the control logic that I'm going to be using on this breadboard version of the build. I'm going to have to iterate several times in order to get to a final solution, so I've decided to use EEPROM for now, knowing that I'm going to have something different when I finally get to the PCBs and what would be the final iteration. Here I've got my code for just the basic control logic that I've got so far. Right now I've got, from the EEPROM, I've got 8 bits of output, and I've used all 8 bits so far. To walk through this code very quickly, first of all, I'm using a .cc, which is a C++ extension, and I'm compiling it using C++, but the reality is this is really written as C code, and you can more than likely get it to compile without any issues using C. Up here I've got some defines for some of my control lines and exactly which lines would be active given any particular signal. And so what I've done is I've gone up here and set up the things that I need specifically for a no-op instructions. My address bus 1 assert program counter, my and latch the program counter, my do nothing and load and increment and decrement of the program counter. I called your attention that the increment is not 0. Do nothing is 0. So it's not like I can have just straight zeros all the way across the board for my control logic to guarantee that a no-op instruction is zeros. I've got the size of the EEPROM. Right now I'm using a 32 kilobyte EEPROM, or 256 kilobit. And so right now I've got a 8-bit output, and this is my EEPROM buffer size. And then so now we get down into how we're going to generate the actual data that gets written onto this EEPROM. In my main entry point here, I've got what is basically a loop through all 32K bytes of the EEPROM. And using that particular byte position, I am going out there and generating a control word. Now I'm assuming I'm getting back 64 bits worth of data, which I am then going to turn around and stuff into this prom buffer. But at this point, I'm only using the bottom 8 bits of that. So that will expand out as I move along. So for every possible control signal combination, I'm calling this generate control signals function. And this generate control signals function's up here. I am masking off the high 7 bits of the location, the memory address location, or the instruction location, and the low 8 bits of the actual instruction. This will come into play later, but I am defining this no-op instruction, the control signals associated with that, such that a no-op will assert address bus 1, or I'm sorry, assert program counter to the address bus 1, increment the program counter, and latch the program counter. And then for every possible permutation of these control signals, it just simply returns a no-op instruction. That means that my entire control logic, for no matter what I feed in as far as its control logic is, the instruction is concerned, and its additional control flags are concerned, no matter what it gets, it's going to return back a no-op instruction. This is a huge step towards being able to free run this CPU as it stands right now. A couple of other things. I've got a make file here. My make file is generally just a wrapper to call tup. Now, what I will do later is I will add other things into this make file in order to provide other things. So if I want to make and load it onto the ROM, it will call minicom, which will launch the communication software for communicating with my TommyPROM. And then this tup file down here is actually the build instructions. Now, why do I not have this in make, or the make file. I am not a huge fan of make. I have had problems with more complicated builds, making sure that everything actually does get built. Now, that's probably not a defect on make's part, it's a defect in my ability to use the tool properly. Regardless, this is a simpler solution for me, and it pretty much guarantees that if I can get it to build once, it will always build and always build what is necessary. So for me, that's easier. I don't have to put as much brain power into the tools that I use, and I can put more brain power into the solution I'm trying to develop. How you read this is a build instruction that takes all of these as inputs, pipes it through this particular command to arrive at this output. And actually, if you see it up here, EEPROM is the name of the binary that I am producing. And so if I was to call EEPROM, it will actually just run it. I don't have any kind of greeting or anything like that, but it does create this control1.bin. Whereas if I look at the control1.bin, it is updated as of today and the current time. So this is its output. Now, to take a look at that, and I will make this the larger screen, you'll see that everything is not zeros. It is quite literally all the value 2, meaning that coming back and comparing to my constants up here, my high order bits are 0, meaning I'm asserting the program counter to address bus 1. My end latch bits are 0, meaning that I am going to latch the program counter. And then the lowest 2 bits are 1, 0, indicating that I'm incrementing the program counter. And so that's the control logic that needs to now be programmed onto the EEPROM. This code for the control logic is available on my GitHub site, and I'll provide a link in the description. A while ago, I had a TommyPROM that was on breadboard, and I converted that to PCB. I'll link to the video up in the corner. And I have not yet applied power to it, which I have been able to do now. And in order to test this, I use Minicom in order to get my connection. So once I have this connection and the TommyPROM actually boots, this information is now coming from the TommyPROM. So the Arduino here is actually what's performing all of that. And if I reset it, it basically reboots back to this point where it's waiting for commands to come through the serial line. What I need to do is I need to take this EEPROM, which is a 32K EEPROM, drop it in here, making sure my little notch here is up at the top, and lock that down in place. Make sure that it is unlocked. Make sure that I can program to it, because several of the EEPROMs come shipped already locked, and if you don't unlock it, you're not going to actually get anything. And so I just need to write the control logic to that. And so to do that, nope, that's not what I wanted to do. That's it. X modem, and then I need to go down to my, well, hang on a second. Space tag, but I am not, oh, I have to hit space twice. That's why. Okay. Projects. And so there it is, writing that. It is sent. What I probably should do is I probably should dump the EEPROM, so from 0 to, let's say, 100, and that shows that it all got written 2s, which is appropriate for this. So that tells me my TommyPROM is working correctly. That also tells me that I was able to program my control logic for anything that comes in as the instruction register to be interpreted as a no-op instruction. And so now I just have to put this into the build so that I can test this in the build. All right, before I go and plug this in, let's take a moment to reorient ourselves as to what we're looking at here. This is my prototype register, and I'm going to use this as the program counter for now. This is my stand-in for memory. I joke that this is carefully architected such that every single memory address contains its own address as its contents. The reality is I've just got the address bus 1 assert lines looped all the way down here, coming onto this breadboard here, which is my address bus 1. which is right off the bottom of the screen here. Address bus 1, temporary, which then drops onto this board, which is my temporary memory. Basically, it's jumped right into the fetch register. And then at the top of the fetch register here, I have my control logic here. Now, my blue breadboard here is just a connection point, and then down here I've got the clock. I have not yet applied power. And so I had to sit down and think about the order in which these connections are made, and I don't have any notes that I referenced. I just went right off the board here. This isn't good. This needs to be connected to the clock. Well, that was fun. I believe I've got over here the red line, which is this one here on the corner. This is my clear, and then going into the first two addresses of my 74LS138. I'm sorry about the hot spot here. The light's in a bad spot. 74LS138 here are my do nothing, increment, load, and decrement lines. So those are right next to it. So those would be these two black lines, which are coming off this 08, which the 74LS08 adds additional delay onto that. Then I believe the next two in line over here become and latch and address bus 1 assert, and then these 5 over here are the other 5 different buses that we're not playing with, so I've got those tied high down here so that they're not asserting as well. So if that is truly set right, then when I apply power, what I should see is the the instruction here. I should see the program counter incrementing and latching, and I should see the fetch register showing each address in turn as it increments. The address here will increment, and then the fetch register will increment, and then the instruction register will increment all in succession. And its starting point is not guaranteed to be 0, so we could end up with some crazy starting point, but it should increment from there. Well, that ain't working right. Let's see here. What do I have wrong? I've got a ground line that has popped out up here. I have a ground and power here, which isn't going anywhere. Let's tie those into here. No need for power here. Let's see here. I tied clear low. I should tie it high. So I have some signal that's messed up somewhere. So let's see here. Okay, that's correct. So this is my assert. My assert is not asserting. All right, let me grab my logic tester. So what this tells me is I probably am not outputting correct signals off of here, because if I set this to be outputting and well, I'm not sure. There may be something else going on here. So let's see if we can trace this down. This is currently... Do I not have power to this board? I do not have power to this board. Well, that would certainly explain a whole lot. You'd think I would have thought of that. So amazingly enough, if there's no power to the board, ICs are not going to work right. No ground. Let me get ground in here. Okay, I've got some floating inputs over here. Something is going haywire, which isn't correct. And it could be simply because these two lines are swapped, where I'm trying to load floating lines and latch them. So let's clear that up. And whoa, we started counting and then we stopped. All right, something is not going well. Something's still floating that shouldn't be, or I have some bad connection somewhere. And unfortunately, I have to move this around so much that it could be just about anything. Okay, so this is incrementing properly. Oh, it does not like my hand in there at all. All right, so what are we looking at here? So now, if I touch this, I see that I've got a floating input. Clock is stopped. Is it my imagination, or are these floating around a little bit? Yeah, these are changing. Low, 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 low. Okay, that's output. That should be bit 0, bit 1, bit 2, 3, 4, 5, 6, and 7. Meaning this is backwards. Or my input is off. Okay, that's high there. So that's my input 16 bits. That's high. That's high. So that's where that is. So something's going on here. Because I've got low, 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 but I've got up here, low, high. So where could this be pulling high from? Let's see, it's all part of this node. Let's disconnect this and see what happens. That's low now. Oh, I pulled the wrong one. Something upstream is causing it to go high. Let's see here. That would be this. Okay, I got multiple paths of power there now. So now the next question is am I asserting? That's high, that is not asserting, and it should be asserting. So do I have this incorrectly? So that's low, that's low. Is my clock working? Clock is working. That's low, that's low. So if this is constantly low, this should be what is asserting onto the bus. So this should be the assert. This should be that assert. That's high. That's high. That's high. I bet you this is low. That's low. So I have this wired backwards. So let's take this one out of here and put this one in here. So I have to make some notes as to which way this is all hooked up. That's boiling down too. So this should now be low, which it is. Which means I should be able to find this address out here. So low, 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 low. That is not correct. Okay, that's high. That's low. That's high. It shouldn't be high. Did I not have that right? I had that right to begin with then. Okay, so this one's tied low. It's this one I've got to measure, and that's high. So this should be low, and it is. That's low, and it is. That's high. This is one of the problems you have when you walk away from your build for a month. Okay, that's low. That's actually properly low. And that's low. No, yeah, that's low. This is going to be high, high, some fluff here, or dead bug. High, high, high. So if this is low, I have this backwards. I genuinely do have backwards. And that should be floating now, which it is. And going back here, that should be high now, which it is. Now going back up here, that's high. That should be the low, which it is not. And that is low. So why is that not making a connection? Do I have a dodgy cable? If that's the case, this will be the end one here, the end one here. This one is showing up here. That should be low. So which one is now low? That one's low. This one. All right, let's put it in here. Now it's low. Other than the fact that I've got something floating happening over here. This bugs me. I gotta figure this out and why that's actually doing that. Because the latch is an HCT, so if it's got a floating input, it's gonna create problems. The rest of them are LSs, which are gonna have pull-ups. Something over here is not connected well. That seems to have stabilized somewhat anyway. My hand is not creating problems. No, there it goes again. All right, so not hooked directly into my power here, and so maybe I need to drag some additional power connectors over. That ain't gonna work. Let's see if I can find a longer. Wow, I don't understand why that's scrambled like that. So my reset is not firing, so I don't have a problem with power because my power comes in up here. It jumps down here to this board, comes around through here, and then it's quite far away from where the power is delivered. Am I getting an or load when I shouldn't be? That is floating. How can that be floating? Because I don't have a ground line actually hooked up to it, that's why. That's interesting. So this ground line over here needs to come over one. And now I need to put this back in the right spot. So this is now connected to ground, which is it should be. This is now 5 volts, which is as it should be. I just had this ground line here in the wrong spot, causing this to produce floating output, which now should completely stabilize this. I gotta figure out a way to debounce this better. Alright, so if you notice here, I've got 10101 in the lowest 5 bits, 10100 in the lowest 5 bits, and 10011 in the lowest 5 bits, meaning that this is one step ahead of this, which is one step ahead of this, which is exactly what I need it to be. And so this is quite literally the CPU free running, meaning that I do not have anything that I am doing to control the fact that this is incrementing, and I'm not tied directly into the clock. These control signals here, these control signals are all being produced from the control logic up here. This is a free running CPU, meaning that the CPU itself is executing instructions. Now, Is it meaningful? No. Am I stretching this? Probably, yeah. And so the next step is going to be to take the memory module and expand that so that I can actually put some code on here. And then when I can put code on here, then I can actually start writing some programs that will manipulate some of this as well. When I do that, I do plan on pulling this. I haven't disassembled it yet. I do plan on pulling my other register back out because the thing I need to do is I can't increment with this. But what I can do is I can load it, and I will start working on loading the register with values. So after I get the memory module taken care of, I should be able to actually program the computer to load this register. And again, I don't have the replacement for it yet. I haven't ordered those yet, but I'm getting close to the point where I'm going to need to do that soon. This will make another appearance in the build before it's all done, and in the meantime, this CPU is, in my opinion, free running. Now, I had a comment from Mats Engström, I believe I'm pronouncing that right, and if not, I apologize, related to the falling edge being heavily averaged, or the yellow trace being heavily averaged, whereas the blue trace was not. And I was able to find a couple of things. I was able to find my original documentation, which is amazingly light in quality documentation. But I was also able to find some information online as well. And the challenge is nothing really talks about averaging. So nothing I really did here made a material change in the quality of these traces. The other thing I did try to do is I tried to swap the probes, meaning that I went from one measuring point to the other measuring point in an effort to see if the problem followed the probe or if it remained with the pin configuration that I was plugging into, and it remained with the pin configuration I was plugging into. So the probes themselves, the settings of the actual probes really have nothing to do with it. This is really more of a measurement of what's going on the breadboard. The final thing I did to clean this up a little bit is, and as I pull that off, is I switched the probe to 1x instead of 10x. And obviously I made the same change here on the oscilloscope. And that seems to have made quite a difference in the quality of the trace that I was measuring. My original thinking was that 10x was a measure of the probe sensitivity, and I've now come to realize that this oscilloscope has the ability to measure up to 400 volts, but it can only do so if it's in 10 times mode. Actually, it's up to 1,000 volts if you have probes that will do 100 times. But the typical 1x is up to 40 volts. Since I'm only measuring 5 volts nominally, it makes more sense to have these probes set to 1x, and then I get a what appears to be a much cleaner trace. So, Mats Engström, thank you for the question. I'm not going to answer every question in video form, but I wanted to make sure that I circled back on this and touched on it real quickly, just because I am learning, and this was a great experience to have to do this research and troubleshooting. Thank you. We'll see you soon.